will start with introducing our first speaker. This is Dr. Eshan Dawe, who is a colleague of mine. He's an associate professor at UNH, and he will be discussing density measurement of asphalt mixtures and pavements using a dielectric measurement system. Dr. Dawe.
Thank you, Joe. So thank you very much for this invitation and for giving an opportunity for us to come here and talk with you about some of the work that we are doing on this topic. Again, in theme of UTC in general, presentation here, I'll try to focus a little bit more on what we are doing in terms of taking research and then trying to help put it into practice. So that's really the focus here is what all steps we are going through and taking a tool or set of tools that have been developed recently and helping them adopted into everyday construction practices for asphalt pavements. So it's really a joint effort together with Professor Sayas on two different projects that we have. So I'll very briefly talk about both of them. And then if you have any questions, we can obviously elaborate a lot more during the actual Q&A or the discussion session. Also, I should acknowledge Ann Tran, who is the graduate student who has been working with us on this particular topic, who has really been the force behind a lot of stuff that you'll see here. So as civil engineers or people involved with transportation, most of you may be very well familiar with the need for trying to control density or air voids in our asphalt pavements. Air voids is one of the most commonly controlled parameter in all the quality assurance processes that we are currently using for construction of asphalt pavements. And there's good reason for it. That level of air voids has a significant impact on the durability and longevity of our asphalt pavements. That's why if you pick any of the state construction specifications, and you can see an example here for the 6 New England states, those are the parameters that are currently controlled within those states' construction specifications as items that really your pay factors depend on, or items that really dictate whether that project is accepted or not. And one thing that you'll see throughout there is air voids or the density level is common. And that's not just these 6 states in New England. That's pretty much every 50 state or every public agency that you have across US and even internationally. And as I mentioned earlier, there's good reason for it. I mean, I just borrowed one of the plots that you see here. There's more going on in there, but it's really the point that plot is trying to make is that there's a certain density range depending on the size of mix and so on, which impacts the permeability of your asphalt mixtures. And asphalt mixtures are expected to be impervious when they do become permeable, not by design. There's a whole area of pervious pavements and porous pavements. But when they are supposed to be dense graded, and yet you have these connected air voids, it really sacrifices the durability of these mixtures. So how do we measure what is the level of density or air voids in these asphalt pavements? At least what's the current process? And so the current approach, at least in field, is to oftentimes go and do coring, where you are actually taking out samples of asphalt mixtures from your pavement. And then you are bringing them into lab and you are applying really a basic gravimetric analysis. We use the dry weight, submerged weight, saturated surface dry weight. So it's a very standardized process, really nothing unusual there or very simple physics principles there. However, the challenge is you have to go out and actually take these measurements or take these specimens. The alternative to that has been developed and has matured very well in the last 20 years is nuclear density gauges. These are great devices. They are really using a nuclear source and a receiver to try to relate to the density of that asphalt mat. However, the challenge is the word nuclear, which means they are actually regulated by nuclear entities. There's a very specific training that's required for anyone who's using them. There has to be a custody requirement, so these can only be stored in certain places. Every lab that has to have a dedicated space to store them, and everyone needs to be keeping track of that nuclear source and so on. So those are some of the challenges in the current practice. The other thing that I'll also mention is both of these techniques, coring and doing a direct measurement, is obviously gold standard, right? You are actually measuring density of that material. However, that's a spot check. You can only take so many cores, and if you try to make a Swiss cheese out of your pavement, no one's going to be happy. So they don't want you to take too many cores. And you need multiple pieces of equipment in lab as well. You have to have a temperature controlled water bath to do submerged weights. You have to have oftentimes a vacuum sealing based method, which has become quite standard in the asphalt industry. So there are challenges with the current approach. And that's where the research or the technology or the innovation comes into play. And I can take no credit for development of this technology. This has already been developed through efforts of previous researchers. But that's the dielectric measurement method, which is really the same technology as ground penetrating radar, which is very commonly used for pavements as well as geotechnical applications. You really are shooting electromagnetic waves into your pavements or into your bridges or even soil. And you are really looking at those velocities and reflections, generating a plot similar to an example that you can see there from the Min Road facility in Minnesota, where those reflections can tell you a lot about thicknesses of layers, if there are delaminations between the layers, if there's any moisture present within or between the layers. The idea behind what you see in this presentation is to take that same technology, miniaturize it, and also make it more suitable as a quality control or quality assurance tool. And that's done with the development of what's now referred to as the density or dielectric profiling system. Why this method works? Because what you are measuring through this is a dielectric constant. Every material has a dielectric constant. Water has significantly different dielectric constant or higher value, and that's why microwaves work, right? When you put stuff into microwave, if it has higher amount of moisture, it heats up faster. Air has significantly higher dielectric constant than solids. And so since we are interested in air voids or density of asphalt mixture, we can utilize this measurement of dielectric constant as a way to determine what is the in-place density of our asphalt pavement. So the change that we are looking at is really, instead of having to take these destructive core samples or use non-destructive technique that still only works in a spot checking type of manner, convert to a more of a complete coverage type of approach. And you see a device that is really initially developed originally through a SHARP 2 effort and then matured by a company. And now there's a pooled fund that is led by Minnesota Department of Transportation into this density profiling system. And I believe our third speaker will also talk a little bit more about it. You can see an example of that in North Dakota, where it's been run over a pavement. And what you see there, 3 different bands, is actually not these 3 different antennas, but 3 different lanes that have been constructed side by side. And you can really see right off the bat that there's something going on at specific places, right? Wherever you see the significant changes in the dielectric values, that means that either you have very high or very low density spots that have occurred as a result of your construction practices. Now, if you had relied on your original method, there's a chance that you may not actually end up taking cores at those places, and you would never know about these non-homogeneous or non-uniform locations within your construction. And this is much, much faster than either of these 2 processes. Literally, you can do a 1,000-foot section and completely scan it in matter of minutes, as opposed to taking several minutes just to get 1 core with the current approach. There's also similar change on the lab side of things, where once again, we can replace our standard AASHTO process that requires a specific gravity bench, which means you have a scale with a suspension system that you can use to get submerged weights and oftentimes have the vacuum sealing method to get your densities. That all can be replaced by this simple single piece of equipment, very small, can be easily set up into the construction trailers that can be brought to site and easily take the measurement. Same technology now, instead of taking the density or measuring in situ density, we are measuring density of these specimens in lab. So there's two different efforts that we are working on right now. One is an IDEA project that's sponsored by National Cooperative Highway Research Program. And what that project focuses on is how do we take this existing technology and write a standard specification, AASHTO specification, that agencies can then take and adopt and put into practice. And along the way, we are also developing some machine learning based models because what we are measuring in lab is a dielectric constant, and we need to have ability to go from that to density. We can always do some calibration curves, but we are trying to get to the point where we don't have to do those calibration curves. For this effort, we actually sampled materials from 16 different states, and what dictated these states is really the geology of aggregate, because each aggregate type has different dielectric constants. So we really tried to go after a broad enough geological sources. We did have quite a bit of material just from New England because that's where we are located, but we are really capturing representative materials across the country. And the study itself, to finalize the specification, we are using more of a standard specimens that typically are used in asphalt mixed designs and acceptance processes. However, we are also looking at variations. What happens if you use shorter samples? What happens if your samples have as compacted faces versus cut faces? Because oftentimes our lab test specimens are chopped out of longer cores. And how does that impact our dielectric measurement? That's just a snapshot of the master data. If we gather all the data that we have collected or measured in our lab so far, some interesting things you can see that these are mixtures coming from New Hampshire and Massachusetts, from as small as 9.5 millimeter nominal max sizes to 37.5 millimeter. But that aggregate geology is so predominant that irrespective of these mixed sizes, they are still following the same trends. And then you can also see, as you look at different type, like marble from Virginia, much higher dielectric values, or trap rock from Connecticut, which has much higher densities. You can see it takes its own trajectory. So in terms of implementation, we did quite extensive amount of testing with all this material to the level where many of these samples we tested 160 times for dielectric measurements in order to develop a procedure that's statistically sound. And what came out of that is a process that has repeatability and reproducibility that would actually be lower than the current density measurement method that AASHTO uses with the specific gravity bench. That means that for each specimen, we are really taking measurement only 3 times at 3 different orientations. And that's really the outcome. We developed a draft specification language. It's submitted to IDEA, and now we are working on the other aspects of that project. I'm out of time or 2 minutes, perfect. So the second project is actually a subcontract to us through a Minnesota Department of Transportation, and it's a pooled fund that has many state entities involved in it, including Maine DOT here. And our contribution to that is really developing a tool that goes together with that density profiling system that allows users to take all the data generated from density profiling system and process it, run basic statistics on it, and also answer some specific questions. For example, there are 3 different sensors on that machine. Are all of those sensors in agreement with each other or not? Or is there a specific bias with one of those sensors? So we already developed the beta version of that tool, and we are going to have in coming weeks actually a demonstration with with the select number of the pooled fund partners, work with them to improve the tool, and really the outcome of this will be something that will go together with the pooled fund effort that agencies can then take and put into practice. But just as an example, it does your basic statistical testing, and analysis, it also allows you to look at what happens with respect to your densities on the mat itself versus near the joints, because joints are oftentimes low density areas. And so you really want to make sure that those joints are getting significant amount of compaction effort. And then, as I mentioned, as part of this tool, we also have functionality that detects the bias. If there is a bias between those three sensors, it automatically detects, and then user has ability to not consider data from that one sensor. Or one thing that we are now looking at is how to correct for, if it's a uniform shift that we always have, can we correct for that shift? So in summary, we have been working on this dielectric lab and field measurement systems as a way to replace or supplement existing practice, because it allows us to have full coverage as opposed to spot coverages of density. It's faster, it requires less equipment. It's especially for field applications. It's something that makes things much simpler. Standardization is important, and that's the aspect that we have been working on, and also tools that can go together with these innovations so that they can be put into practice. So that's my presentation, and I'll be happy to discuss more in the Q&A portion. Thank you.